All right. Hi, everyone. So today we are going to be working with open source data. So that's going to be a whole new exercise, a whole new project that we're going to start today. I just uploaded or pushed some files to our GitHub repository. So we're going to need to download those. You know how to do it. Just go on GitHub, download the repository, bring that into the main folder of the course that you may have on your side. Let me open that up here. So first off, you just download that GitHub repo. I just pushed some files. You can, download it and then move that zip file into the main folder of this course. Remember that 2025 PPA is really, you should be able to delete that from your computer without having any issues because you should not be working directly from that folder. We're just using that to copy and paste those files into your own projects. So if you don't want to be accumulating a whole bunch of 2025 PPA versions, you can just delete the one you have now and then download the newest version, just move that back into the class subfolder or main folder. Once you do download that, before we go inside of that folder to move some files around, I want to ask you that at the main folder of this class, for you to create a new project that or a new folder at this time called 06 underscore open data. Once you create that, if you go inside of it, as always, create the code, data, and output subfolders. Before we move to our studio, I just want to go back here so I can see the 2025 PPA. If you go in there and you go in 04 class code, there is a new partial script for 0204 open data partial. I want you to copy that. So copy that script and then go back and paste on the 06 open data inside of code. So you should see kind of like what I'm seeing, although I also have the completed version of that script, which you don't, but you should have your partial script for open data on the code folder of the 06 open data folder that we just created. Once you have moved this data around, we're going to be going to RStudio to create our RStudio project, right? That's something that we are always doing. So you can just launch any RStudio. It could be a project none. You could perhaps already be in a project. It does not matter at this point. All I want you to do is click on that project, on that top right project icon, ask for a new project, click on existing directory. We're going to browse now to be inside of the, let me see if I can help myself here. Maybe if I come here, teaching. Yeah, so really the main goal is for us to go inside of the folder of this class. And then once you're seeing that 06 open data, go inside 06 open data and stay at this level, right? Don't click any of these folders. Just then click open and create project. This will create a brand new project for us to be working on 06 open data. If you were successful doing this, you should now see 06 open data RStudio project on the top right. And on the files tab here on the bottom right, if you click on code, you should now see your 0204 open data partial. You can click on that to launch it so we can start working with it. Before I get moving, I just want to I know that we did a lot of small steps kind of fast. So I do want to perhaps give you another moment or maybe check if somebody was not able to do the whole setup. But maybe I'll just ask, were you able to do it? Okay. Kiathi and those in Tifton, everyone good to go?
Yes.
All right, perfect. So let's get going. Okay, so here's the font size here. So once you have the script launched, let's get started. So today my goal with this exercise is going to be for us to learn about application programming interfaces, which most people would refer to them as APIs, which is just the acronym for those three words. So we're going to learn about APIs and how to use them to download open source data through R. We're going to use open source APIs to obtain map soil series data from USDA Surgo. We're also going to obtain elevation data for our field through another API, and then talk about map components and how to add those map components to our maps, which is going to be also another important topic for us. All right, so a quick introduction here. If you have never, well, I think Aman, you've been working with Surgo, so you have some idea of what that looks like and what it is. Kiathi and those in person in Tifton, have you ever heard of or have you already worked with Surgo soils data? Kiathi saying no.
Okay. Nope. No.
Okay. All right. So this is going to be a brand new box of a Pandora box here because we're going to unleash a lot of data that is really, really cool. So the United States Natural Conservation Service, so USDA NRCS, Natural Resources Conservation Service. Yeah, NRCS. USDA NRCS, they conduct soil surveys. This started probably in the 1940s or 50s. It's been a while that they've been doing this. And basically, I mean, they did a lot of work that I'll tell you more about, but the product of that work is basically a open source soil series data for the entire US that is publicly available for anyone to use. This is such an important resource that we have here in the US that I don't think, well, we have some other open source data sets for soil across the world, but the US is probably the country that has invested the most on this to not only create soil maps, but also make them available. So the program is called, or the program in USDA and RCS is called Soil Survey Geographic Database, which is also called Surgo. So this is the database we're going to be using today, and it contains information about soil that was collected by the National Cooperative Soil Survey over the course of almost a century. So what happened here is, back in the day, back before we had computers, even back before we had really good satellite imagery to use, these people would go out to fields, would go out to landscape, and they are trained soil surveyors that they would go to a field, collect a whole bunch of soil samples, and create a whole bunch of a characterization of the soil properties that they just pulled, and also bring samples to a lab where even more analysis were being conducted. So we're going to explore this data set, and it's really a very rich data set. It's amazing that we have access to something like this here in the US. This information, it can be initially the way that it was displayed. So if you ever, maybe for research or maybe on papers from the US, you probably have seen soil series or soil mapping units nomenclature. So there is like a Tifton soil series. There is I don't know some of the names of the ones around us here, but basically it's just a soil series is a full combination of soil properties that happen together in the landscape across a larger area, and they just receive a name. So there is like a Tifton soil series. There is a Dothan soil series. There's many, many soil series across the entire US that describe that soil with a name. So you may be familiar with the soil series of your study, for example, of your study site. And if you're not, no worries, because you will be in the next assignment. But basically, we're going to be, this information back in the day was basically published just on paper, right? So like on booklets that USDA would made available. Now, all of that data set that has started to being collected a long time ago is all available online. And we're going to be making use of that data and pulling that data through R. So this data is available as tables or as maps, and available for most of the US, that is served by USDA. So United States Department of Ag, NRCS is the Natural Resources Conservation Service. So again, basically, this information is gathered by the people that were trained to create these data sets, would go out to many fields across the entire US, and then observe soil, observe the landscape, just draw, digitize on an actual physical map, on a paper map, where they thought in that landscape the same soil series that they pull a sample happened across the entire landscape. And these maps, they're basically, so imagine that they would go to a field, maybe one of your research fields, and they would say, well, this soil here is sandier, and this side here is more clay. Let me pull a few samples in each one of those, describe those samples, and then look at this, maybe an aerial image of that field and say, okay, this sample I'm pulling from this spot, the sandy area, is actually on this map. It happens on all this portion of the field. So they would make drawings, digitizing on paper, where they thought that was the boundary of those soil map units. And this information here was collected at different scales, ranging from 1 to 12,000 to 1 to 63,000, in that scale format. Initially, this mapping is intended for natural resource planning and management by landowners, townships, and counties. So these basically, there is a lot of data we're going to look into here coming from this database, but basically they're going to be linked in this database. So both the spatial information of where these soil series happen on a field or even at the landscape. So there is that spatial component, and there is another source of information that is everything that was measured about that soil series. So some things that we're going to have information about is, for example, available water capacity, electric conductivity, frequency of flooding, yields of different crops, and also some limitations affecting development. Again, this Surgo dataset is going to consist of a map layer, which is basically the drawing of where the mapping unit happens, with that polygon shapefile with spatial information, connected to a tabular data that has all the information about that soil series, and some information about how these data was generated. I want to show you here. So again, in the beginning, a lot of this data was collected and it was distributed through just like paper booklets, printed booklets that had this information. So let's say if you are here in Athens, Clarke County, or maybe you're in Tift County, you would call the NRCS office maybe closest to you and say, hey, I live in Tift County, I live in Athens, Clarke County. Can you send me the NRCS soil mapping unit booklet for my county? So you would get the map. You could see what map units happen in your county. Perhaps you could see what were the mapping units that were present on your field, and then use that to make some decision based on those mapping units. Nowadays, all this data is made available through the Web Soil Survey. So Web Soil Survey is basically this dashboard, online dashboard that the USDA, NRCS, Surgo team puts together and publishes online. So I want us to go there on this website now. You can, if you want to do on your side, you can as well. If you just want to see what I'm doing on my screen, you're welcome to do that as well. So I'm just going to copy this address, launch my browser here, and check this website. Even if you could have Googled, if you wanted, you could have just Googled USDA Web Soil Survey, you would get to this place. So this is, again, a website by the USDA. If we click on this Start WSS button, that's going to launch the Web Soil Survey dashboard for us. So you can click on that. It basically launches a map or an interface that looks like this. There's a lot of things going on here. the first thing that I want to show you is, so you could, if you wanted, you could zoom in, zoom out, try to find your field just by visual assessment. But you can also either import an area of interest. So if you have a shapefile or a GeoJSON with the boundary of your field, you could import it. You can give it an address. You can perhaps give it latitude and longitude. So this is what I'm going to do here. I want us to give latitude and longitude first. So we can zoom into the field that we've been working, which is that field in South Georgia. If we go back here to R, these are the coordinates. So longitude is minus 84,76151. This information is in the script if you want to do on your side. So I'm going to give, well, we ask for first latitude. So let's give first latitude, 31.18931. And then comma, and then longitude. So these are the coordinates for our field. So I'm just giving those and hitting the button view. So it brings us to our field. If you remember, this is the field that we're working with. And those were the centroid coordinates that the grower gave us when they said, hey, let's work on this field here for your project. All right, so we established our area of interest. Now what we're going to do is, let me see here, maybe we still have to draw. Yeah, so we're still going to have to make a drawing. So we found where we want in the map, but we will need to have a drawing of the area of interest so we can use that specific area of interest that we give it. So we want to just, if you come here, there's going to be an AOI tool, area of interest tool that you click right there. So we click on it, and then you can just make this rectangle around our field. So I've made that rectangle. This is what is showing that I selected. If you want to, you don't have to be very close. I mean, you don't have to be equal, like exactly the same as mine. As long as you encompass the field, that's the main goal. All right, so now that we've found our field using the coordinates, and then we determine our area of interest after that, we can navigate to some of these tabs. So there is a tab here for soil map. There is a soil data explorer. There's a download soils data and a shopping cart. Let's go to soil map first and see what that is. When we click on soil map, notice that it gives us this information here. So each one of these polygons is a different soil mapping unit behind the NRCS Surgo database. And then it gives us this table here on the left. So this is saying what is the map unit symbol. So this is just a symbol that they use to relate to the specific soil mapping units of your field. Here's the map unit name. So you see here that we have a Goldsboro sandy loam, 0 to 2% slopes. We have a Grady soils. We have a Norfolk loamy sand, a Tifton sandy loam, and a Tifton sandy loam with a different slope. Also gives us here, for this area of interest that we created, how many acres are under each one of these soil series, and then what percentage of the total acreage that we created on the area of interest is represented by different soil types. So for example, we see here that 53% of our area of interest is a Tifton sandy loam, 2 to 5% slopes. Now, another thing I want to show you. So each one of these map unit names, again, these are names that they don't happen just on this field, right? They happen probably in a very large portion of area, maybe in Georgia, maybe across the Southeast. Perhaps there are some soil series that happen even across different regions in the US. So it does not mean that this soil only happens in your field. It's really just, your field has that soil mapping unit in it. So let's say, 53% of my area of interest that I created is Tifton sandy loam, 2 to 5% slopes. Let's click on this. So this is a hyperlink. If you click on it, it's basically going to pull up for you the entire report that describes that soil mapping unit. We're not going to go into a lot of details here, but if you studied soil pedology, soil formation, some of these things should make sense to you. So it is describing the profile, what horizons it has, what is the description of those profiles, what's the depth of that profile, what type of soil texture you have there, what is the slope, depth to restrictive feature, runoff class, drainage class. But really, it has a lot of information here that is related to this specific soil mapping unit. So let's say that in this field here, we have the Stifton sandy loam 2 to 5% slopes. The mapping unit symbol is TUB. Now let's say that we go to another field, maybe in Tifton, maybe one of the research stations, and you do the same thing. You may find the same soil series yet in another field, right? Because that can happen in different places. It's not just this field. And also, this description I'm showing you here is what would be made available through like a booklet that you could get from your county extension office potentially. Now, let's say that I want to explore this a little bit further. So, okay, I know that I have 1, 2, 3, 4, 5 different soil map units in this field. Now I want to get some more data about it. I know there's so much data about these things that I can pull. Let's see what's available. So if you go on Soil Data Explorer tab on the top, it's going to have a lot of different options for us to look into. So notice that I clicked on Soil Data Explorer, and then it opened yet another set of tabs here. So there is a Intro to Soils. I think this one we can basically skip. This is just information for us to learn more about this data set. There is a Suitabilities and Limitations for Use tab. I think that's the one that popped up when we clicked on Soil Data Explorer. So see here that there's going to be things mostly related to, again, suitability and limitations, right? So there is like construction materials, there's going to be land classifications, land management, military operations. You see how this is not made just for ag purposes, right? It is made for soil use in general, which could be ag related. It could also be construction related, right? For different reasons. Very interestingly, there's a soil health option here. So let's click on that and just look into this. Perhaps that's one of the ones that we're going to connect more with what we do. So there's a dynamic soil properties response to biochar. Let's click on that just to see what happens. And then it gives us here, I want that information in map and table. And then let's just click on view rating, see what's going to do. It's basically creating this map for us, showing that basically for the soil mapping units in this field, there are 2 values. One of them is the green, the other one is the red. If we want to understand what that is, we can come on the area below here. So basically we're seeing, let's see, what is it mapping there? Let me just make sure I know. So it is mapping, component breakdown, rating reasons. Let's see, it's mapping something that only has 2 values. So it's probably this one here. Is mapping this column rating. So excellent response, unsuited. So basically just the grady soils are unsuited, which is the red one. Everything else was excellent response. That's what was the response of the soil soil health, agricultural organic soil subsidence, or dynamic soil property response to biochar. All right, I'm gonna close this a little bit. You can see there's like organic matter depletion, soil surface sealing. There's vegetative productivity. Maybe let's look into that. There's forest productivity, Iowa corn suitability range. Let's check yields of non-irrigated crops. Let's look into that. And then I'm going to ask for view description. It's going to make a map for us. So yield of non-irrigated crops is basically has 2 values again, but for different mapping units. So one of the mapping units, the rating is 8.75, whatever this is, and the others are just NAs. They don't have data. Yield of non-irrigated crops at the map units. Yeah, I'm not sure what that 8.75 is. Oh, because it's the crop. So we choose here crop Bahia grass. Let me choose corn and see what corn yield looks like. So select a corn and check view rating. We basically have only values for 2 of the soil mapping units, and I believe this is in bushels per acre. So basically 125 here is for Goldsboro and 110 for Norfolk. I mean, not a lot of variability here, but at least we have some data, right? So a lot more information here that we can play with, even especially if you go on the next tab over the soil properties and qualities. This has soil chemical properties, soil erosion factors, soil health properties, physical properties. There's a lot of things here, right? So I'm not gonna walk you through everything, but I just want you to be aware of this. This tool is really, really great because let's say if you're working with a farmer, for example, when you're doing on-farm research, even before you go to that field, so the farmer just said, "Hey, here's the coordinate for my field." You pull that, bring it into here, or better yet, in R, which we're gonna do next, and you can get all this information for their field even before you go there, right? So this is really, really important for you to plan yourself, for you to be able to place your studies in consistent soil mapping units, and really have a better planning of what you do on the field. One caveat here is that, as you're going to notice on the next assignment, all this data here is started being collected almost a century ago and is still being collected, meaning that you, at least to the extent that I use this data set, I don't really know if this data for my field is it data from last year or is it data from last like 40 years? Like, was it collected 40 years ago or is it collected last year? I, to tell the truth, don't know how old is this data. Meaning that some of these properties here are not super useful if they are more dynamic properties. Like, so there are things, some of these variables like pH, for example, you may get a pH map. We can do that here. Let me do one very quickly just to show you. Okay, we need to determine well, let's get surface layer. So this is a pH map of this field. Now, is this pH map the same as if I go there and pull the samples? Probably not, because this field probably has been managed. It has been, I don't know how old this data is. And even if it was data that was pulled last year from this field from USDA, you don't know exactly where they pulled the sample from. And the delineation of the boundaries of these soil mapping units is subjective to some extent. And so, what I'm trying to say is this is a very useful starting point. It does not replace your own sampling. It does not replace you going there and making sure what you have is what Circle is telling you. But it's a really nice starting point for you to make some plans. All right, if you were doing all this through the web soil survey, you would basically, I mean, we're not going to go through it completely, but there is a way you can select the data that you want to download. Yeah, I think you just select the data, you create a link, and then send to the cart, and they send you an email with a link to download. So that's how you would get a handle of this data if you were doing through their website. I want to show you how we're going to do this directly in R. That's going to be the strength of it. So we can just completely close this web browser. We're not going to be coming back to here. But we're going to be seeing how we can pull this data and make sense of this data straight from R without ever leaving RStudio. All right, so for Surgo data, the data that we were seeing on the browser, we're going to use a package called Fed data. That stands for federal data. That's going to be our API. An API, again, is just a way of you connecting your programming environment on your computer with an open source database that has an API available. So we're going to basically make that connection through R and through the internet without having to go to the browser and point and click. Another piece of field data that's very useful to have when planning that we can also obtain from open source is elevation data. So elevation is really important because it's going to determine how, for example, water is moving on your field, how nutrients may be moving on your field, if you have runoff, if you have erosion potential, and so on. So elevation is a very, very key layer of information that we need. We can create this type of information ourselves. So if you have any equipment that has a GPS that is taking the measure of elevation, you can create an elevation map with that. Most of the precision ag equipment are taking that data. So within any precision ag equipment that is taking some data, there's normally going to be a column for elevation as well. And then you can use that column to create an elevation map. But what I want to show you here is not that. I want to show you a database that is basically already created that we're just gonna pull data for a given field from elevation for that field without having to go to that field and collect the data ourselves. For elevation data, we're going to be using a package called Elevator. That's going to be our API. There is a full vignette for how to use this package. I left you here the address. I'm not going to show you. I'm not going to show you in class, but you're encouraged to explore it if you want to know more. And then finally, this is something that I noticed I was not teaching on previous semesters, and I should have. And so this is going to be something a little bit, well, Neva and Aman, I know Neva was my student last year, and Aman watched my recordings. This is something you have not seen yet. You're probably familiar with it because these are very simple concepts in GIS, but I have not taught myself in my class, which are map components. So we're going to, every good map should have at least these 4 components. That is basically, the first one is the spatial information you're showing, right? So that would be your map, that would be your layer, that would be whatever it is that you're showing. That's the star of the show. But then we need to bring some other pieces of information to make that map really useful. So this would be, for example, if you are coloring different soil mapping units and giving a different color to different units, you need to have a legend. This is for us, we've been doing this most of the time because ggplot gives us a legend by default if you use the AES. But then we also need to have a north arrow and a scale. So I think maybe the reason why I wasn't teaching this in the past is because the default in R and ggplot and map view is to always have the map with north facing up. That's the default. But not all maps are made that way, right? Some maps you may see done in other GIS, maybe people decided to, instead of having north facing up, maybe they flip the map to the side so it would fit better on a page. And maybe north is not facing up, it's actually facing right. So having a north arrow helps with clarifying where that information, right? So you don't have to guess. And then a scale is just an information for us to know how big really that map you're showing is, right? The scale brings you that perspective of how much of a given unit on the map relates to a unit in real life. So we're going to be including those, seeing how we can include those in a map as well. We always want to have these 4 components in a map. Other people in other GIS courses, you may learn to add like a title, for example, to your map or other components. I think that at least the way I use maps, it depends on my audience and my purpose. If I'm publishing a map on a paper, I wouldn't really give that map a title. But if I'm including that in a presentation, perhaps having a title is okay and would help the audience. So it's really, I guess, it's more personal preference in that case. All right, so before we move to the coding side, any questions? All right.
I have a question. If you download the map from this open source data, do you get it like the accurate map, like the one that have been taken by the satellite or any updated instrument, or they use the map they've stored, like the data we have here, they collected many years ago, maybe, or do they based on the data set they have, or they give you the updated map?
Well, we're going to get the most up-to-date version, but that most up-to-date version can be 40 years old, So they're still doing surveys every year. They keep going back to some fields and revisiting fields that maybe have not been revisited longer. So they're trying to update things, but still, if you pull data from Surgo from this field, this may be from like 2 years ago. Then you pull data from a field a few miles away, may be pulled data from like, 40, 50 years ago. So there is that discrepancy. You're always going to get the most up to date, but that doesn't mean that it is the most updated you wish you had, like it wouldn't doesn't maybe the most up to date is 40 years old and they don't have anything newer, and that's what you get. But you're always through Sergo, you're always going to get the most up to date version that they can provide.
Okay, thank you.
Thanks, Paulie. All right, so on the next chunk here, I left you some install.packages commented off. So you can uncomment one of them and run just that line. Do not run the whole chunk because is not what you want at this point. So install the elevator package, and once it goes through, comment it off. I think I already asked you to install the package stars. So maybe you can skip that. Install the fat data packages, the patchwork package, and the ggspatial package as well. Do one by one because if you have issues, it's going to be easier for you to identify it that way. But I don't think you're going to have issues installing these packages. They're pretty straightforward. As you're doing that on your side, I'm going to keep talking. And when I get to the end of this chunk, then I'll ask if anyone needs more time. So once you finish installing all these packages, then we're going to load them. So tidyverse, it's that family of packages that has dplyr, tidyr, ggplot2. So we're just using loading tidyverse for that. SF is that package that we use to handle vector geospatial data, like polygons and lines and points. MapView is that package that allows us to do interactive maps. Elevator is going to be the package for open source elevation data. Stars is the package that helps us with vector geospatial raster data. I'm sorry, vector, not vector. SF is vector. Stars is raster. So SF, vector. So SF would be polygons, lines, points. Stars is raster. So raster would be either an image, like an DVI map, or any layer that's continuous in space is going to be raster. And we'll talk more about what I mean by this. But in this case, elevation is going to be in a raster format. So that's why we need this package. Then the package fat data to obtain the open source soil series data. We're going to use the package ggspatial to add map components of legend and north arrow. We're going to use ggthemes because it has a theme map that helps us with the ggplot theme that's more clean for maps. And finally, we're going to use patchwork, which is going to be a package to help us combine multiple plots into a single plot. All right, so if you were able to install these packages above, you remember that you want to either comment off, or you can just delete the install.packages function if you wish. Just go ahead after that, and then you can run the whole chunk for the library functions just to load all those packages. We always get some warnings and messages here, but I don't see any error message, so that's the key thing. It's just this first warning is from tidyverse, and then we have something here from SF. Yeah, we have the fed data. Okay, so I think there was this is awesome. So when there's a point of this script that we would have to use the SP package instead of the SF. And now I'm seeing here this message from the fed data saying that they have retired dependencies on the SP and raster packages. All functions return Terra for raster and SF for vector. So that's great. That's an updated from their side that was not there last year. Okay, so a quick check-in from my side. Was somebody not able to get to this point? All right, I don't hear anything, so let's move on. As I was telling you on maybe last class, having a field boundary is one of the first steps in Precision Ag workflow because that's going to allow you to first to know where a field is, but then to pull open source data if you want, like we're doing here, or other reasons that you may need to know data about that field. So we're gonna, first thing here is if we want to pull open source data, we're gonna have to bring in our boundary. So on this next chunk, let's do that. Now, before we go full throttle on what we're gonna be doing on this chunk, I just have a question for somebody. It can be anyone. What function would you use to bring in, to read in that boundary file that we created last class, that you digitized last class? What function we're looking for here? Can you say that again?
Read the shape file.
Okay, it is a read function, but it's not called read shapefile. Any other guesses? Okay, so someone said read SF, right? So let's go and call read SF. Remember that even though on file, like on your computer, that layer is a GeoJSON or a shapefile. In our case, we export it as both, I think, but we're gonna bring the GeoJSON. In R, when it comes into R, it becomes an SF object. So that's why we're using read SF. Open and close quotation marks here. So we could have done a couple things. We could have copied that boundary GeoJSON from the previous project, the 05 digitizing project, and pasted that inside of a data folder of this project. We could have done that. But I decided to just pretty much go back in code to that project and through code make that importing from that other project instead of moving files around. So that means that we have to get outside of the code folder, // If you hit tab, you are at the main folder of this project, but we need to get outside of this project. So // Now you should see all the projects that you have on the class folder. We're going to go inside 05 digitizing, hit tab again, go inside of, let's see, I think we had it on output maybe. Let me try. Yeah, so go on output and then boundary GeoJSON. That's what we want to do to bring in our boundary. So if you run that, you should now have a boundary object in your environment. And let's just print a boundary right here so we can check. So it is a simple feature with one feature, two fields. It is a polygon. It is WGS84. That's all looking good, right? It looks like our actual boundary. If we want to do a quick map just to check, you can just call a map view here and do boundary to see if that looks correct. It does look correct, right? If I change to S3 world imagery, it is the boundary I created on my side last time. Remember that each of us created our own boundary for this field, so maybe your boundary looks a little bit different. That's not a problem. It is a problem if you have a completely different field, or maybe, when Luke was initially digitizing and he didn't have the base map behind, that could have been an issue as well, but I believe Luke was able to fix it and get the correct one. Okay, so now we have our boundary. The next step here that I want us to do is going to be to pull Sergo data. So this is the exact data that we were seeing on that website interface. It's just that now we're going to do this in R. So I want to call this object soils. We're going to give the assignment symbol. There's a function called get _ SS Sergo. This function is from the fed data package. So the first argument here is going to be the boundary that we have. So here we're just going to say boundary because that's the object that we just imported above. Let's give it a comma. We're going to change a few arguments here. So one of them is the argument called label. So this is how I want the data to be, what's the name of the folder I want this data to be saved in my computer. I want to call this Sergo. I want to give it a comma and change yet another directory here. So basically this function get Sergo, it will download to your computer the data for this field. So the data is in the cloud and it will basically download that data to your computer. And then we're going to use this data from there. So here, what we want to do is that there is an argument called raw.dir for raw data directory. Let's give it quotation marks. I want to get outside of the folder that the script is in, so // I want to go inside of the data folder, / I want to call Sergo, which is the label that we gave above, / I want to type raw. So raw is going to be the name of the folder where the raw data will go, and then /. So yours should look something like this. This is the directory that we are telling Sergo, the get Sergo function, to save the raw data in our computer. Then there's going to be one last argument that's called extraction.dir, the same thing. So it's going to download raw data in a zip format, and then it's going to unzip for us by itself. We just need to tell it where to put that unzipped version. So again, quotation marks, .. data / Sergo / and then let's call it extract. I'm just gonna give you a quick moment to catch up here. Once you're done, make sure that your directories are correct. Oh, I think we need maybe a / after extract. So once you have all that in place, just go ahead and run it. I ran before when I was testing the script, so I'm gonna already have it. I'm gonna delete from my side so I can rerun again with you all. All right, so if you just run that, it may take a moment here because it's basically downloading all that data for us, all the data. So it's downloading first the shapefile with the different soil mapping units for the field, and then it is downloading all those different pieces of information that were on the web soil survey to your computer as well. So it is a good amount of data that is downloading. So it may take a moment here to go through. Once it's done, then it says downloading circle data for survey area, and then gave us this code, downloading file, and then just gives us what is the file that downloaded. So basically what we just did here is if you had gone to Web Soil Survey, brought your area of interest, clicked a whole bunch of icons asking for a whole bunch of data, and then click on the export and download data, this is what you would have done manually there. Here, we're just seeing how to do that in R very quickly, I mean, relatively quickly, without having to leave R. Now, if you want to print soils, I guess if you haven't done that yet, don't do it. Or maybe we should do it. Yeah, maybe we should do it just for the sake of it. If you print soils, it's gonna be a lot of stuff. So basically, we downloaded this data from Sergo, and it did save that to our files, to our computer, but also assigned that to this object called soils. So if you print soils, look at how many tables, data frames it has for us. It has a lot. It has basically, I don't know how many data frames here, but a lot of data frames that are each one connected to a different part of Web Soil Survey that we were checking. All those menus and all those tabs, it's all here. So now we have all that. Our soils object, so the object that we assign all this data, has two main components. One is the spatial component, which is where all the spatial information is. And then it has a tabular component, which is all these tables here. So let's first explore the spatial components.
Sorry, can you go back to the script because it's not working for me, and so I want to check if it's
Yeah.
right.
So this, and just a quick tip here, this works well if you are in the 06 Open Data project, right? Remember that we use project because it helps with relative paths, which is what we're doing here. If for some reason you're not in the 06 Open Data project, that could be a reason why it may not be working, but it could also be something else.
Yeah, I am in the folder, but it still doesn't work. I don't know why.
Does it give you a specific error?
He say unused argument label.
And you're using the get Sergo function?
Yes.
So maybe try to just, well, first off, is this same issue happening with other people?
For me, it's working.
Okay. So Benedetta, what I would say is, I mean, I'm not sure why this is happening, but it seems like it's not. Oh, make sure you have a comma here
Yes, I do.
and at the end here.
Yes.
Okay. So if you have all that, then try to just comment off this argument. So that way the function is going to ignore it. Let's see if that works.
Still doesn't work.
Okay, I'm not sure what's going on. I think maybe we're gonna have to get on Zoom to look into that. And so I don't think we're gonna be able to troubleshoot here in class.
I think have you installed all the package?
Yes, I did.
Did you
Okay.
try loading each one at a time rather
Yes.
than the whole chunk at a time?
Yes.
So I think that was the package you said we installed, but we've not actually installed it. And for my case, it wasn't working. I went back and wrote all the package.
That's good. So Benedetta, one thing that Neva was saying here is, so this is, I guess, really the only thing here that it would need to make sure it's the same is that the script is in the code folder. So when you do a // you get outside of code, and then that's your data folder that should name the same way as I did, lowercase. If you named like uppercase D data, then then you need to follow the way that you did on your computer. If perhaps that is the discrepancy.
I did tab, so it should be correct, but I'll
Okay.
figure out. Probably there is a misspell or something.
So I think let's do this. I think we're gonna keep moving just to make sure we go through the material. If you cannot like find out what's going on your side, then maybe now in class you're gonna have to watch, I guess. You can still code along because the code is gonna be the same. You're just not gonna be able to run it. But when we figure out what's going on, then it would work. And then we can connect with you. Neva can try to help you initially to troubleshoot this. Yeah, you can open an issue on our GitHub repo with the like a screenshot of your code and then a screenshot of the error message, and then Neva's going to take a look at that while we keep going. All right, so besides Benedetta, I think everyone else was able to do it. So we were about to explore the spatial component of this soils object. So if you just type soils, give it the $, you see that it has a spatial option. If you click on that and you print it, this is basically an SF object. So it is an SF object of type polygon, WGS84. And then on the data side, it has 5 columns: area symbol, spatial layer version, MUSYM. This stands for mapping unit symbol. Remember that symbol that we saw on Web Soil Survey? That's it right here. And there is an MU key, which is the mapping unit key. So this is both the symbol and the key are 2 unique identifiers to a given mapping soil unit. And then it has a geometry. So these are so the key here, the mu key, is what we're going to use to combine the spatial information, so the polygons, where they are, what are their boundaries, with the tabular information. Very similarly to what we did with the county data. Remember that the county data, we had the tabular data in one place, and we had the polygons in another place, and we joined them through a common column, which in that case was the county name itself. Here we're doing the same thing, but using the mu key, the mapping unit key, as the common layer. One way, again, that we can check to see if this is working or if the spatial data makes sense, because right now we're just looking at the spatial objects, right? We're not really mapping it. I always like to map things, so we can call a quick map view here and give it soils $spatial. Look at that. This is actually really, really interesting. So this soil spatial is actually not just our field. It is a whole bunch, it's a larger area that is basically comprising our field. So I just changed the base map to Esri. And I think if we zoom in, so our field is right here. But the soil spatial is a larger piece of land. It's basically the units that our field is within. So it gives us the whole soil series for all that. Meaning we're gonna have to do some clipping. We're gonna have to clip all this information to only contain our field at some point. But anyways, nonetheless, our field is fully represented within that map. So that's great. All right, so on the tabular side, as you notice, there's like all these tables, all these data frames with different tabular information. So one way for you to quickly check what is in those layers is if you type soils, $, there's the spatial and tabular, right? So now if we go on tabular, if you give it another $, it's going to show you each one of the columns that you can get from there. There's a lot of information here. Remember that all of these things are all the information we had on Web Soil Survey. And you remember it being so many tabs and items that you could select, right? So all of that is right here. Without knowing what all these names are, it's going to be difficult for you to really know what to do or which of these data frames would be useful. I want to propose we look into 3 of them: component, MU AGAT, and MU crop yield. So the component one, if you just start typing components, it's gonna fill in for you and you print it. So this gonna have, so it has 109 columns. This is crazy, right? So 109 columns. This is how much information you have here. So see that there's a component name. This is the name of the series. It has what kind it is. It is a series. If there's a flag, I think this is probably something related to data quality. Slope low, slope mean, and slope high. I mean, there's like runoff, so very low, negligible, medium. There's just there's 109 columns with information about these soil mapping units in our field. A lot of stuff. I'm not going to go through all of them, but just wanted to make you aware there's a lot of information here. If we check the MU aggregated component of the tabular piece, so MU aggregated, and you print that, notice that this has the mapping unit symbol. It has the mapping unit name that we saw as well on Web Soil Survey. And it has some other data that is aggregated across all soil depths. If you go to the Web Soil Survey, you could get data for specific depths if you wanted. This MU aggregated, it just means that's aggregated across all depths. So just get one value of whatever you're looking at per soil series. So there's like flood frequency, ponding frequency, available water, not sure what the AWS is, but available water something at a specific depth, I believe. So there's like a lot of information here as well, 40 columns that you can look into. And then finally, I want to look into MU crop yield. So remember that we were looking into the different crop yields on Web Soil Survey. That's that data right here. So we have what is the crop name, what is the yield unit. So this would be bushel or pounds or AUM. I'm not sure what that means. But then there's a non-irrigated yield lower, a non-irrigated yield R. So this R is basically the mean, and no irrigated yield high. So what would be the low, a medium, and a high value for that? We have irrigated yield as well, and then the mu key, which is that connecting column that we need to have. And just to remind you, there's a lot of other data frames with their own columns inside the tabular. There's a lot of stuff, right? We're not going to use all that. I just wanted to focus on these three to give you an idea of the most common ones that we could use, but there's a lot more. If you want to know exactly what these different data frames and what these different columns are and mean, I left you a website here. So there's an NRCS PDF that describes this entire data set. So if you have, let's say, let's go there very quickly. And let's say here that I want to, I want to find maybe where can I find clay information? If I just search for clay, it finds here for me. So on the sea horizon data frame, there's a column for clay total. Low R is basically the mean and high. So if I want clay, I should go to that sea horizon data frame. So if I come back in R, if I come back here on tabular and I do sea horizon, there is a tabular data frame named sea horizon that if I print is going to have that information for me. So again, there's a lot of things here. We're not going to go, check this out, 171 columns of information. It's a lot of data. So I just wanted to give you some idea of what's out there. And if you're looking for something specific, you can look into this website here that I just showed you, and you can find it. We are going to focus on the MU aggregated and MU crop yield first. So our goal next is going to be basically to combine the spatial component. So remember that soils object has a spatial component and a tabular component. That tabular component has, I don't know how many data frames in there. So we're going to take some of those data frames and connect that with our spatial component. So we can actually map that tabular information. So if you come, well, before we start doing that, any questions or issues about this?
So I close R and I open it again and it worked. But now I have a problem with the map view spatial.
So you have a problem with what? Can you say that again?
So it worked, the one that I had a problem before by closing and opening R again. But now I have a problem with map view $symbol spatial.
So when you
So,
soil,
okay, I just lost that part.
okay, so when you type soils $spatial, it doesn't give you this?
No, because I wasn't able to do the whole code now. Thank you.
Okay, nice. Nice, thanks, Benedetta. Thanks for sharing. Yeah, I mean, sometimes, I don't know if I told this class or the other course that I teach, but, I don't know, 90% of computer science problems can be solved by rebooting your program, your computer, the internet connection, whatever. So I think that was the solution here. So I'm glad it worked, even though we're not sure why. Okay. So again, the what I want to do next is to connect the spatial information with the tabular information coming from Circle. Circle does not give us those two things connected already. They give those components separately, and then we combine them ourselves. So if you come here in the next chunk, I left some code here. So we are going to create a new object called series SF. We're going to start off with the soils $spatial. That soils is the object that we have. The $spatial is basically that SF object that has the spatial information but doesn't have a lot of data. So this is what that is. So we're going to start here. I left you that piece of code, and then I left you some comments that we're going to be coding along. So add a pipe right next to soil spatial, go after the transforming. Well, you know what? And this is something interesting. Last year, when I did this exercise, the fed data was still using SP package and object types to relate them to SF objects. So last year we had to take this step here to first transform from SP to SF. This year, we don't have to do it because they just updated, I mean, they updated since then their package and they're not using SP anymore. They're already using SF. So actually soils $spatial is already an SF object, which was not last time that I did this exercise. So we can basically skip this transforming from SP to SF. I'm just going to delete that. Well, as you know, I like to have my column names all lowercase, and so I want to clean up those names. Very easy question here, low-hanging fruits. What is the function name we use for that? Okay, so I'm on here. Yes, go ahead.
I was going to say the package from the janitor package.
Yeah. Oh, and that's a good point because I don't think we loaded the janitor package in our first chunk. So we either should do that, or as you all know, we can just call explicitly janitor, colon, and then clean names. That way we don't have to load the package because we're just calling a function from it. So if you run that and you print series F, it is still just that SF object with the column names all lowercase at this point. All right, sounds good. So now we want to join this with the mu aggregated tabular data. Let's give it a pipe, come after that comment. What function did we use last time when we joined the county spatial data with the county tabular data? What did we use for that? I think Amon has the answer. Let's see if somebody in Tifton can help me here. So when we have two data frames that we want to join, they have to have a common column. Both the column name and the column levels or information under the column should match. And then we do a left join, right? So we're going to use the function left join here. So basically what comes on the left is what is coming through the pipe. And then what we're bringing from the right is going to be the tabular data. So the tabular data, the way we're going to call it here is going to be calling the object name soils, give it a $. We want to go into the tabular component of that object, give it another $, and bring the mu aggregated data frame. If I just print soil $tabular mu aggregated, it's just this. It is a tibble with 4 rows, 40 columns, and it has the mapping unit symbol, mapping unit name, and then a lot of information. And I think in the end, it has the mapping unit key, perhaps. Yeah, it has the mapping unit key at the end. So we're going to do a map join, left join, sorry. And if we just run it, let's see if it can figure out which column is going to use by itself. Okay, it was not able to match because there is an incompatibility in type. So we found a matching column, mu key, both in X and Y data frames. So X would be coming through the pipe, Y would be the one we gave in left join. But it's saying that in one of the data frames, mu key is a character, and in the other one, it is a double. We can fix that. However, we can also try to join by another column that is a character in both data frames, which is the mu sim, the mu symbol. So here on left join, we can give it a comma and we can say by. So which column I want to left join by, it's going to be equals to mu sim. Let's try that. Okay, no errors, so we can try now to see. So we have an SF object with 6 rows and 44 columns. So we have all that data, and now it worked out. So we basically looked at the mu sim column, and it joined by using that column for us. So it worked here. Now, if I were to just do a map view on series SF, just for us to double check if what's going on, it is still that that data frame that, oh, sorry, that polygon for the entire region where these soils happen, and not just our field. Our field is there, but I don't really care for the entire region. I want to basically clip all this data frame to only contain our field. So then we're going to add a pipe, come after the comment here of the cropping to the boundary. We're going to use a function called st_intersection. Make sure you select intersection and not intersects, because they're two different things. And we're just going to give our boundary. So if you run this, and now we check a map view of series F, just like before. Now we have all the soil mapping units just for our field, which is what I wanted to have. Was everyone able to get to this point?
Can you go back a little bit to the code? Okay. Yeah.
All right, so it's starting to shape up like what I wanted. On the next chunk, I just want to make another map view, but then color those polygons using the mapping unit name. So let's call map view, give it the series underscore SF, give it a comma. There is an argument called Z pol. We've used this before, so this is not new to you. And then we're just going to give the column that we want to color by, which is mu name. And this is what we get. So we get a map and a legend for the soil mapping units with their names for our field. So we see there's 1, 2, 3, 4 soil mapping units, just like we saw in Web Soil Survey. This is their name, which basically describes what is the series name, what is the series texture, and what is the percent slope of those series as well. All right, so we made this interactive map, which is kind of cool, but I do want to have a static map that we can export to file and then, perhaps include in a presentation, include in a paper, so on. So let's come here and create a static map of the same thing we did above. I want to assign this our map to an object called series map. So that's why I left that name there. You can just give it the assignment symbol. We're going to start off with a ggplot call. As always, right? As we've been using ggplot for our plotting purposes. So I want to add a plus here. The first thing that I want to bring is this object right here that we just used, which is called series SF. What function do I need here in ggplots to bring that layer? Kiathi, what do you think?
I forgot, I'm sorry.
That's all right. Let's see, Luke, what do you think?
I've also completely forgotten. I find it, but I forgot as well.
Polly, what do you think?
Can you repeat again the question?
So we want to make a static plot of this object, which is called series SF. What is the function we need for that in ggplot?
I'm not sure. I don't remember really good.
Benedetta, what do you think?
Oh, I have no clue. I'm struggling follow up.
Come on, what do you think? Geom? What? Yeah, Geom SF, right? So it is an SF object. Remember, SF objects are for vector spatial data. When we're making a map of it on ggplot, we need to use Geom SF. So here we're going to say data equals series underscore SF. If you just run that and you print your map, this is what it's going to look like. All right, so now I want the fill of those polygons to be mapped according to the column mu name, right? If I want to reproduce, sorry, this here. How do I do that? It's gonna be inside GeoMSF, right? So how would somebody do it? What do you think, Polly?
I'm sorry, I wasn't following. I was struggling with the code above and did not get the question.
Okay, so let me ask you something else. Do you need to check my code, or do you need some help?
It's just I was a little bit behind. There was a code that gave me an error, and I went back to fix it.
Okay.
So I was a little bit behind, but right now we're at the same stage.
Okay, perfect. So let me repeat the question then. I
Yes.
want to basically reproduce this map, or at least parts of this map, where we're given the fill of the polygons according to a column. How am I going to do that in GeoMSF?
Can you use AES?
Yes. So
Yeah.
AES, right? Because we're mapping an aesthetics, in this case, fill, to a column, to a variable in our data set. So it needs to be inside AES because of that reason. All right, so what would you say here?
Field equal to series. This will be equal to series SF. Field equal to series SF.
So series SF is the name of the data frame, right? We already specified that right there. Now we need to tell what column we want to fill by.
Oh,
Let's use here mu name. We have this column that inside series SF, we have mu name. Let's do that. So if we run this and you print it, now we get that, right? So now each one of the polygons is colored or filled according to their mu name. Okay, the next thing I want to do here is I want to change this color scale. I want something that is colorblind safe or friendly. So we add a plus, and we've been using this function a lot, so I hope that you're thinking about this. But we're going to use the scale underscore fill because we're changing the fill, so it has to be fill underscore Viridis, and I want to use Viridis D for discrete. Run that, and you print it. There we go. Now we change to a colorblind safe scale. Also, I want to use the theme map, which is just a simple theme that works better with maps. So let's add a plus. Theme underscore map is going to change some of the features of the overall map just to make it looking more like a map. Now, something that we're noticing here is that theme map puts the legend right on top of the map, which I dislike. So I want to move this legend to the right. I don't know if we've done this yet or not, but we're gonna use, so we call these functions theme underscore something when we want to change all the settings within that theme. In this case, this is theme map. Now, if I want to be able to change something specific about this map, I need to use the function that is just called theme. Inside of theme, I have a lot of options. If you hit tab, there's going to be a lot of options for you to change. What I want to change is the argument called legend.position, and I want to give it the value of the word right. So it moves the legend to the right of the map. Like this. All right, so this map is starting to look better. Now I want to show you how would you add a north arrow and a scale to this plot, to this map. So after that theme, let's add a plus, hit return. There is a function called annotation underscore scale from the GGSpatial package. let's just run it to see what happens if we don't change any of the behaviors. Okay, not too bad. I mean, added a scale to the bottom left of this plot. So that's okay, that's good. This function has a lot of different arguments to customize this scale. So for example, I don't want it to be every 100 meters. I want it to be every 200 meters instead. So I would come here on annotation scale. I would change the width. There's an argument for width underscore hint. And I'm going to give it 0.4. This is just a way of us changing the width that we want to have on that scale. So now it is 200 meter scale. There are many things you can change about this. I'm not going to show you all of them. You can, if you want to place this scale in a different part of the plot, you can look into the help of this function and you're going to find how to do that. Actually, you know what? I'm just going to remove this argument with hint and just leave it as is because I think it's pretty straightforward. It was in a good place. It was not overlapping with anything else. So I'm happy with it. All right, so we added a scale. We're missing a north arrow. So let's go ahead and add a plus, hit return. There's going to be another argument for annotation underscore north underscore arrow from that GG spatial package as well. Let's just run this as well and see what the default behavior does for us. So we place this north arrow right on top of the scale. It's overlapping a little bit with the scale. And also, to tell the truth, I think this north arrow symbol is kind of ugly. So I want to change a few things about this north arrow. So one of them is I want to come here and it has an argument for style. And here you can give different functions that will produce different north arrows. The way, how do I know all this? Is because I was doing help annotation north arrow and reading the documentation. That's how, if you want to change some of these things, you can change a lot of things about the scale and north arrow. Just ask for help on those functions and read the documentation. It's going to give you all this information. So if I say style, it has a function for north arrow fancy orienteering. That's the function we want to call. You don't have to say anything inside the function, but if you run it and you print it, then it changed our north arrow a little bit, or it changed the symbol, but it is still on top of our scale. I'm gonna change I'm gonna try to change the placement of our north arrow to be a little bit more upwards, a little bit more to the north. It has also here this annotation north scale function. So let me just do this so you can see. So this isn't a full argument. It has another argument for location, which is the location of the north arrow. And if you look into the documentation, you can give it values like bottom left, bottom right, top right. You just give the initials. So if I want bottom left, which is where it is at this point, just to show you, if we run that and we print it, that's where it is. We could place it maybe top left. Let's see, so TL would be top left. It's still on top of the map. We could give it, let's see, BL for bottom left. Oh, that's where it was, sorry. So bottom right, BR for bottom right. Okay, so I mean, it's kind of overlapping. I don't know if I liked it or not, but we can also do top right, TR. Okay, it's still overlapping. Let me see. I think one thing that we can do here is maybe let's keep it bottom. So BL, bottom left. So it is going to overlap a little bit with our scale, but I want to move the north arrow a little bit up. To do that, it has another argument that is pad underscore, it has a pad X and pad Y, depending on which direction you want to move it. We want to move it upwards, so that's going to be pad Y. And then we give it we call a function unit. So we're going to give a value here. Let's try 0.1. And then we need to give what is the unit we're using. So let's say cm for centimeters. That's how it will look like. So that is not, I think actually, I'm not sure if it went up or down. Let's try 0.5 centimeters and see which way it moves. Okay, so it moved up, right? So it's not overlapping anymore. We can even do like 1 centimeter perhaps. Yeah, that's okay. I like that. So this is how we would move around. The same pad Y and pad X exist for the annotation scale if you wanted to move that around. So this is how we would kind of customize what you want to do with them. All right, so our map now has, we have the map, we have the legend, we have a north arrow, we have a scale. So we're good to go. I like it. Is it working? There's an error?
Yeah.
What is it saying? Okay. On Zoom in Tifton, was anyone having issues? Okay, so let's keep going. So we just made a map of the soil mapping unit or the soil mapping series of this field. We get some information about their texture. So there's sandy loam, loamy sand, sandy loam. So overall, they're pretty sandy soils, and they have different levels of slope, right? So we're seeing here that we have 2 to 5% slopes on the Tifton sandy loam, which is the yellow one. So as kind of a sloped field here in this case. So the next thing that I want to do is very similar. However, I want yield information for this from the Circle data set. Remember that we had like a non-irrigated yield for different crops when we looked on Web Soil Survey, and also here on the script. That's what I want to pull here. So we're going to call this object yield SF. I left you here the starting point, which is the soil spatial. If you remember, this is an SF object that only has very limited soil information, but it has the mu key and the mu symbol, and it has the polygons as well. We were transforming that from SP to SF. Again, this is not required anymore, so you can just delete that. We are cleaning names like we did before. And then now I do want to use the mu key. If you remember the mu key, when we did that before to do the join, the left join, we got an error saying that one of the data sets mu key was numeric, on the other one it was a character. So I'm just changing here mu key from soil spatial. Right now, I think that's being interpreted as a character. Yeah, so it is a CHR column. I'm just changing that to numeric by doing this. Then we're doing a left join with the soils tabular in mapping unit crop yield. If you remember, we saw this before. You had the crops, it had yield for irrigated, non-irrigated crops in different crops. We're merging them or doing the join based on the mu key column. And then again, doing the intersection on the boundary. So we would only have data for our field and not that whole region. So if you run all this, and if we print, so I got a warning here, but we can just ignore that. If I print yield SF, so it is an SF object, so we have the polygons, that's what we wanted. And then we have here, if you just scroll, non-irrigated yield lower, non-irrigated yield R is for the mean or median of the field, and then a non-irrigated yield high. We also have a column for crop, because all of these rows are referring to different crop types. Let me see, where is that cropping? Okay, so there's a crop name column. So there's yield for pasture, corn, soybeans, wheat, tobacco, peanuts, and so on. So I want to select only a few columns here to make it simpler. And also for this exercise, I just want to keep corn yields. That's what I'm most interested for this exercise. So if I just want to select some columns, what function do we need here? Do that again. Okay, so Amandeep said filter. Does somebody agrees or somebody disagrees, has a different opinion?
I think it's select.
Yes, in this case would be select, right? Thanks, Kiati. Yeah, so if we are taking a subset of columns, we want to use select. If it is a subset of rows, then it is filter. We're going to actually use filter in the next step. Yeah, but here to select just a few columns is going to be select. So let's call select from the dplyr package, as I always tell you. So dplyr : select. I want to keep crop name because I just want to keep corn, so I need to have that column to filter by it. I want to have, so let's see, I think it has a units column, so we know what is the unit of that value. So crop name, yield units. And then we're going to take the non-irrigated yield.r, which represents a representative value of the field, which kind of means it kind of has the implication of being the mean of that field or that mapping unit. So non-ir yield.r, and then the geometry column, which in this case here is called geom. So I want to just keep those columns for now. You can just run it and you print it. Now we still have 36 rows. We just have 4 columns, which are the ones that we kept. And now, as you can see, there's data for non-irrigated yield mean for a lot of crops. I want to just keep corn. That's just a arbitrary decision that I just want to look into corn. So let's give it a filter. So we give it a pipe and then filter where crop name equal sign to corn, and corn has to be C uppercase because that's how it is in the data frame. So if you run all this and then you print yield SF, now we have only 4 rows. And just where crop name was equal to corn, and then we have the non-irrigated yield mean with 4 rows for this data set. All right, so the next thing is I want to make an interactive map with map view. I left you the code already, and I just want to create that non-irrigated yield color of the mapping units. So if you just run that, this is what you're going to see. Basically, there's only 2 mapping units that have data on corn yield, and those are the 2 ones that we have data for. One of them is 110, which is the purple. One of them is 125, perhaps, which is the yellow. So really not that much interesting, for at least not for this specific field. But you know, this information is going to change from field to field. So perhaps on your fields, it may be more interesting than what we saw here. Then lastly, I left you all this code because we already did very similarly to the other data sets, is just creating a ggplot to create this map above. So if you just run that and then print yield map, this is what you're going to see. I decided to not put a north arrow and scale on this map for a very specific reason that you're going to find out at the end of this exercise. All right, so we basically finished with retrieving Surgo data for our field and then making a couple of plots for this field. As you saw, we could have made hundreds of different plots for this field with Surgo data. We have so many variables. I just selected a couple that I find interesting, which is soil series name, texture, and slope, and also the potential yield of a crop that can be high yielding for this field. We don't have all the information for all soil mapping units. We had for a few only. So this wraps up our Surgo API. We still have the elevation API to go through. So before we switch to the elevation, any questions?
Dr. Bastos,
Mhm.
my plots are something different from the one you got. I don't know why.
You mean on the first map that we made? On this one?
No, no, no. The last one. I have a complete gray and black plot. I don't have the yellow part there.
So you do you have these two colors different?
Yeah, like it's completely black. I don't have a yellow colored zone.
Everything is black?
Yeah,
Hmm. Interesting, because
I don't know. Can I see the code?
yours the same, Aman?
Yeah.
Huh.
It's showing gradient,
Mm-hmm.
but one part black and other is like the
Huh.
yellow is not.
Interesting, because this piece of the code, I actually left this for you. So
No,
you
no, not. I don't. That's not the part. The next part.
the like before this,
No,
maybe.
no, the one after that. Yeah, yeah, that one. Can you?
Yeah, sorry, let me leave it here.
Yeah.
So is anyone else in Tifton having the same, like where everything is black?
No, it's the same code. I don't know why.
So Amandeep here in Athens is having the same issue as you, Kathy. So I'm gonna quickly go to her computer and check. And
Okay.
then if I find something like by taking a
Okay.
look, then we can talk about it. But otherwise, we can maybe revisit afterwards. Let me quickly go to Amandeep's computer.
Okay.
Let's see. I think that's it. I mean, but this one works.
Yeah, but
Yeah. Let me die. All right, Kathy, at least for Amandeep. The reason why it was
Mm-hmm.
black for her is here on the filter, she had only one equal sign. Check if
One
you,
sec. I think I got it. Yeah, I got it. I missed a pipe.
okay, you missed it, yeah. Yeah, yeah, I think, I mean,
Thank you.
you should all have the same, but yeah, so it's really, yeah, it's interesting because, so both you and Amandeep having the same outcome, but in your case, you missed the pipe, and in her case, you missed an equal sign. So, you know, fun programming stuff that you can get the same problem in different ways.
Yeah.
All right, so I mean, we just have, because we're going to 4 today, right? Yeah. So I don't want to keep you for too much longer. So let me just tell you here, make sure you save your script. Next class, we're going to continue this script here, and I think we're going to probably finish very quickly. We're just going to pull elevation data and then make some maps. And so we should, yeah, maybe 10 more minutes, we would have finished this. So we'll finish on Thursday. I thought that we were gonna finish today, and in that case, I had a new assignment for you all. Because we did not finish today, so that assignment, I think I made it due on Monday of next week. Because we're gonna basically be finishing this exercise only on Thursday, I'm gonna push that a few more days as well. So if you're already seeing an assignment about open source data due on Monday, just want to let you know that I'm gonna have that push forward a couple more days for you to do so until Wednesday. Let me get your attendance. So GitHub 5 PA. Attendance February 4th. All right, so make sure that you claim your attendance. I'm gonna stick around for another moment here if you have any questions, but if not, I'll see you on Thursday.